Let's talk about memory allocations. C gives us two choices when we reserve memory. One is through static allocation, which is what we call memory allocations on the stack. Another through dynamic allocation, which is what we call allocations on the heap. These are two different memory locations. And in this video, we'll talk about memory management, how we allocate memory, how we use it, how we deallocate, how we allocate, and in general, how we manipulate memories all throughout. So we'll keep it at a high level and introduce a couple of functions that we see in C that allows us to manage memory. So generally, when we are talking about memory management, we're talking about memory allocation. So when we, for example, declare an integer a on the stack here. So this does not involve any new in C++ or malloc in C. It's simply just declaration of this variable 4 bytes on the stack. And this is being allocated statically, at compile time. So there's no dynamicness, to it. However, let's say if we allocate this pointer, using malloc, at some point, and this involves the use of allocating, 8 bytes, because a pointer occupies 8 bytes on most of the machines, modern machines. Then this memory is coming off of what we call heap. This is what we call runtime, dynamic allocation, which means, at runtime, we can dynamically allocate or deallocate, a segment of memory somewhere. So this is very useful, when we have something in motion. Static is where we declare something, let's say declaring or define something. This involves the use of defining variable, defining arrays, defining pointers, defining streams, so on and so forth. This is the static memory allocation, and everything else, that happens at runtime using malloc. This is what we call dynamic. So this is a general some kind of split between the two. We're going to talk about this and this in more details. Everything runs on memory, including our mains, So this main is literally just a function and a whole bunch of other functions. This is all part of the program. So in fact, when a function calls another function who calls another function, each function actually occupies some memory. And this is all part of the program memory. So conceptually, this is definitely not in stone, but conceptually, if we look at, part of memory being reserved for, running the program itself, the other part of the memory, would be data storage. So we can have multiple global variables, even local variables as well. We can also have initialized versus uninitialized variables. So in, some textbook, if you go into this topic deeply, then you'll see stack, and you will see heap, you will see a section. This is all part of the conceptual view of the memory, and this is more of the detailed view, and this is the high level view, right here. So they're different. So stack, heap. Sometimes you have what we call BSS. This is for all of the uninitialized data, So like if you said integer a, and that's it, integer a, declaring integer a, there's no initialization. It simply gets put inside a BSS section. You have also initialized data, as in, let's say integer I equals 5, So this I gets set what we call the data section, DATA, not to be confused with this data, So these are two different conceptual views. You can also have, this is the text area. So by and large, there's multiple sort of conceptual compartmentalizations of areas of your memory for storing different things. So this is stack, this is heap. And from a data perspective, you have global variables. So this could be static, Again, this static is not the same as the static memory we're talking about, but simply a static variable, which connotes to this variable being one of the only one at any runtime. So we'll get into that in more details later on. There's also obviously a place for heap, a place for stack, and this is all part of your kind of the data portion for storing, variables, pointers, arrays, so on and so forth. We can refer to memory allocated in the heap only through a pointer. What does that mean? Let's say if you have an integer pointer p. Well, in C++, right, you will see something to the effect of this, right? However, in C, right, we write like this, right? We use malloc, right, as opposed to new. And remember the use of malloc, right? This guy right here, and in C, right? And this is in C++, and the use of new. These are keywords. In C, this is a function. In fact, new is actually a function as well in C++. Both of these, right, connotes to memory allocation through heap, meaning if you look at your memory cloud, there's a large portion of it being the heap memory, right? And stack is like right here, like a small portion of it. Whenever you use new, whenever you use malloc, the information is coming off of your heap, okay? Your data is coming off of your heap. This is involving the use of pointer, right? This is the reason why we dynamically allocate information off of heap through use of a pointer. This is a very interesting diagram. Let's look at static memory allocation. On latter part, we're going to talk about dynamic memory allocations. On the static side, every time you declare a local variable, right, even if this variable is global, it doesn't really matter. You're ascertaining, right? You're getting the information off of what we call stack, okay? Same thing here. When you locally declare, right, or even globally declare an array of 3, this ARY itself, this is an array of 3 elements, right, integer elements. This entire array is sitting on the stack, right? Like I said, there is no, right, new, right? There is no malloc, right? There's none of that stuff. We're gonna look at, and this is actually C++. This is C, okay? Or calloc or realloc. I mean, it's a whole bunch of, we'll review that later on. All right, so let's look at dynamic memory allocation down there here too. Now, this very first line is an integer pointer. Now, this very first line is an array, right? Pointer pointing to an array. Now, this entire pointer itself is also allocated off of stack, okay? So is this ARY is off of stack. So what's coming off of stack is that 8 bytes, right? What is that 8 bytes? Pointer is 8 bytes, right? So this is 8 bytes. In fact, you can do a size of, right, X, and this will actually give you 8 bytes, okay? And size of ARY will give you 8 bytes. So that entire 8 bytes coming off of stack, okay? But now, interestingly, on the very second line, we said malloc, right? Malloc means allocating dynamic memory and assign the pointer to that allocated space. So there is that allocated space right here with a memory address, 0 times FA1. 0 times FA1 is return, okay? 0 times FA1, which is an integer that's returned to X. So X is the pointer that stores what? An integer, which is someone else's memory address. That memory address came from heap, right? Same thing with your pointer variable ARY, which is calloc. We'll talk about calloc later on. So essentially, you're asking for some amount of information coming off of heap, right? And this information has a memory address 0 times ZK1. So this function actually returns a memory address that got allocated in the heap, ZK1, back to ARY. And ARY is a pointer that stores that information. So even though ARY itself on the very first line is declared, right, off of stack, your memory that ARY is pointing to is coming off of heap, right? So this illustrates, how memory is retrieved, right, off of stack versus heap.